Now we will consider the effects of uh, background flow or fluid flow, right? And that is something we have already discussed. What happens in such cases? So whenever there is velocity in the fluid, it actually enhances the rate of mixing, right? And when I say there is velocity, that means there is advection. Advection is something that you're transporting fluid from one point to another, but within that process the mixing between the uh, solute and fluid gets enhanced, the rate of mixing, right? And it is much faster than what happens with molecular diffusion. And we discussed that already here in this example, right? In this one, this is with molecular diffusion. This gives you this small mixed zone, but for same time, if there is this background flow, right, we are assuming that the porous media is moving, this whole thing is moving from this to this side. In that case, you will have this much thicker mixed zone, which is greater than L1 for the same given time. Okay, and this is happening because there is fluid flow or there is advection, which actually converts molecular diffusion into mechanical dispersion, right? And that's why we are considering the case of Peclet number much greater than 1, where most of mixing happens with dispersion, right? So here let's consider a similar case that we studied before, right? This is 1D flow, okay, where C is equal to 0 before T equal to 0, right? But now we assume that there is a flow happening. So now the complete fluid is moving from left to right and there is a velocity u. Okay, so this is moving with velocity u at all times, right? And now at a particular time at t equal to 0, apart from the velocity, we also started injecting some concentration C naught, right? So velocity is there, but you are also injecting, let's say you inject some dye in water, the flowing water, right? So what happens, it starts mixing with water, but at the same time it is moving. It's not just mixing at that location, but with the background velocity it is also moving, right? And this is what happens in case of groundwater. Groundwater flow generally happens continuously, or groundwater is usually flowing. There is always some sort of gradient, and that's why it keeps flowing from one point to another. And if there is some contaminant mixing in groundwater, that does not mix locally, it actually advects from that point to another, and while it keeps mixing with a broader and broader mix zone, right? And that is what's happening here. This mix zone that you see here is actually broadening. So earlier that was a small mix zone, now you will see a greater mix zone. This is becoming larger and larger. And if you want to plot the concentration profile, it will look probably something like this. So concentration towards x equal to 0, if this is x equal to 0, will be almost equal to C naught, but as you go away it will decrease and then it will become equal to 0 completely, right? And here this will look something, right? It will be little broadened than how it was before, and in case 3 it will be broadened something like this. So it will have much larger mix zone than previous two cases, right? And what happens in all these cases is this middle point where you can assume the concentration to be 0.5. So let's say you define C hat to be C over C naught like this. Okay, and at this point your C hat will be roughly 0.5, C hat is 0.5, C hat is 0.5, and that is the location with which your fluid is actually moving. So if you define this as the point, that will be x equal to ut, if this is t1, so that is x equal to ut1. For this one it will be x equal to ut2, here x will be ut3. Okay, so this is a t2, this is a t3. So what you see here at these locations x, that is the location of the advection or advection front. Okay, and that actually you multiply velocity with time, that is the point where fluid, this dye will have moved after time t1 or t2 or t3. Even if there is no mixing, even if there is no dispersion, this fluid or injected fluid or concentrated fluid will still be moving, right, regardless of mixing. But now when mixing is happening, it is also kind of spreading on both directions, right? So at this advection front, where which is defined as x equal to ut, this is you can call this as advection front, the concentration can be considered equal to 0.5, or C hat can be considered equal to 0.5 at advection front, right? Because that is the mean value of the concentration C naught and concentration 0 of the ambient fluid. Okay, and now we are going to derive a solution for this particular case by assuming that concentration is 0.5 at the advection front, and we will see how this concentration varies both to the left and to the right. So we will do a change of frame of reference. So instead of considering from x equal to 0, we define eta equal to x minus ut. Okay, and we say that at the advection front your eta is 0, right? At eta is 0, and to the left eta is negative, to the right eta is positive. Okay, and for this we try to find the concentration profile, and we are not going to do the full derivation here, but the formula that we get in this case is given by C hat is equal to 1 over 2 ERFC. This is the complementary error function that we have defined, ut over 2 dt plus half e to the power x u over d ERFC x plus ut over 2 dt. Okay, so this is the concentration profile you get in this flow when there is velocity happening, right? When there is velocity u. All right, and d here is the dispersion coefficient, which is actually defined as some alpha u, where alpha is the dispersivity, and because u is constant here, this is basically the constant velocity, d here is considered constant in this case, and that is why we take it outside the differential equation and we derive this particular equation. Okay, so this is the concentration profile you get for different values of x and t, and this is by assuming eta equal to x minus ut. So what you can see that this has this particular function inside error function, and here you will see there is this minus sign here, whereas there is this plus sign here. So what actually it means is, with increasing time, the second term or value here inside will keep increasing, whereas here the influence of ut will continuously decrease. And that is why at much larger time what happens is this particular term becomes much smaller, right? As you can see, when that value increases, this ER of FC becomes very small for very large value of the value within the bracket. And that is why for large time, when t is much greater than 0, this C hat can be written approximately as 1 over 2 ERFC x minus ut dt. Okay, so this is the concentration profile. This is an approximate value for much larger than 0 time. Okay, so now if you want to plot the concentration for this particular case which we are considering, it will look something like this. So if you want to plot it against eta, right, and you define your C hat as something like this, so it will look something like this. Okay, so you can say this is at time t1, this is at time t2, this is at time t3, and this is eta equal to 0 or x equal to ut. So at eta equal to 0, your concentration is 0.5. So here you can say this is C hat equal to 0.5, or in other words, your C is equal to C naught by 2. All right, so you can see how this with increasing time the concentration distribution is spreading or is getting widened and widened. Okay, and if you want to do it without changing the frame of reference, it will actually look something like this. So this is your C by C naught, and let's say this is your x equal to 0, and this is also your x equal to 0, right? That is the location you're trying to plot from there. So your original concentration will look something like this, right? So that is let's say this is your t equal to t1. Okay, and then if this is your t2, then here the concentration distribution will look something of this sort, and if you define this as t3, this will broaden even further. All right, so now just by using this particular equation in defining different values of t, you can find concentration at different values of x, and this is your x. Okay, so these concentration values that you get is with advection when the complete fluid is moving with certain velocity, capital U, and this is more realistic case in case of groundwater flow, right, where we are not assuming the contaminant to be fixed at a point, but it is advecting from one point to another with certain velocity. Okay, so this is still a simplified case because we are considering one-dimensional model, right? Here this flow is still 1D, but now if you want to study the same problem in a 2D geometry, when you have you consider that there is a continuous groundwater flow, right? This is let's say some seepage velocity or something, and you have a source, so you are injecting some C naught here, okay, which might be coming as a part of some leakage of contaminant or something. And now because there is continuous injection, and this is a two-dimensional geometry, now you have consider this is x, this is y, so this concentration that you have will actually spread something in this manner, right? It will not go just straight in one line, but it will spread both in x and y, and likewise if you consider this problem in three-dimensional, it will spread in actually more in a cylindrical form, or at least in axisymmetric form. All right, and that is why to solve this problem, now we will make one simple assumption. The flow is running for reasonably long time such that early effects are not important. Okay, and we consider only the steady part. Okay, so we are basically neglecting the unsteady part or transient effects of this mixing. We assume that this has been going on for a long time, and this concentration profile or this spread, okay, that you see, or this is also called the zone of influence or dispersion, has already been formed. Okay, in that case, the unsteady part in the dispersion equation will not really be important, and that's why we are considering the 2D medium. And if you try to write this equation, dc by dt plus u dc by dx plus v dc by dy should be equal to d square c by dx square plus d square c by dy square, and we are assuming d to be, let's say, constant for simplification. Here we assume that the velocity, background velocity, is only in x direction. Okay, so u is equal to u in x, but v is 0 in y, and only the advection in x direction is important, and advection in y direction becomes 0. So that particular term is not important. And also, as we have studied that or considered that steady part is the only thing we are considering, but unsteady part is not important, and that's why we consider this to be 0 as well. And that is why this equation can now be written as u dc by dx is equal to d square c by dx square plus d square c by dy square. All right, and now in this case we can make further assumption that, as we see in this image, right, or this diagram, with long time when the flow is completely developed, we assume it has become long and thin. Okay, this is a long and thin zone such that your x length scale is much greater than y length scale, right? And this is something we have done in the past for this kind of flows. So x length scale is much greater than y length scale, right? Because flow is primarily happening in x direction, not in y direction. And that is why by scaling analysis we can say that d square by dx square is much smaller than d square by dy square, right? Because y value is much smaller than x value, and that is why this equation can further be written as dc by dx or almost equivalent to d square c by dy square. Okay, so this is the advection dispersion equation we want to solve. Okay, so this is a simplified equation, as we have discussed different conditions for which we are able to find this equation, and now we want to solve this for finding concentration profile, where you can see C here is a function of x and y, whereas in previous equation, in the diffusion equation you saw before, C was a function of x and t. Okay, so now if you solve this equation, this will give us the concentration profile of the form C hat is equal to 1 over 2 ERFC y over 4 dx over u. Okay, so this is the concentration profile you get for this particular problem, where d here is again the dispersion coefficient, which can be defined as alpha u, where alpha is the dispersivity. Okay, and you can see how C hat here is a function of both x and y, and C hat we know is C over C naught. So this basically will give you C as C naught by 2 ERFC y over 4d x over u. Right, and now for a particular x direction, so if you are solving it, so this is a point of injection and this is the zone of influence, right, and this is the direction of the flow. So we have defined this as x, this as y. So if you find, let's say you define this as x1, this as x2, and you define from here this is positive y, this is negative y, right? So if you can see, this is your y equal to 0 line, right? And if you look at this equation carefully, for y equal to 0, your concentration is simply C naught by 2. So for y equal to 0 line, you have C hat equal to 0.5, right? That comes from this equation. And now if you want to plot the concentration profile, here your C hat will be 0. This is the line of C hat equal to 0.5. The outside again C hat will be 0. So if you want to plot your concentration, it will look something like this. Right, this is C hat equal to 0.5 and it's increasing, and you try to measure from this green line. This particular line is measured from there. Likewise, if you plot from here, this will look little broadened like this, but here C hat is again assumed to be 0.5 and C hat here is 0. Right, so you can see how your concentration is spreading both in x and y direction for this particular setup. Okay, so now this same problem can be again solved in case of 3D geometry, where z will be there as well, but that will again require some more mathematical details. And so far the problem we have considered are without considering the effects of gravity. We assume that this flow is happening just in horizontal direction, not in vertical direction. But when we consider the effects of gravity, when the flow is happening in vertical direction, this what you see here will be slightly different. And that is the next problem we are going to study, because the groundwater flow that we are considering here does not really happen only in the horizontal direction, but it also happens in vertical direction, right? Or there might, or basically groundwater, even if that's happening horizontal direction, your contaminant transport might be happening in vertical direction. So there is always some effects of buoyancy or concentration gradient in vertical direction that we need to consider. Okay, so far the results we have derived for one-dimensional diffusion or one-dimensional dispersion, and then this is two-dimensional dispersion with advection, are without considering the effects of gravity. So let's now move to the vertical flow, where we consider gravity in form of buoyancy or plumes.